When can you reverse a function? You might think, always. Just swap the inputs and outputs. But watch what happens here. We have 4 different possible inputs and 4 outputs, and their corresponding mapping. If we were to switch the inputs and outputs, so having x, which was our inputs, be turned into the outputs, and y being turned into our inputs, so reversing all these arrows, all of a sudden, we would no longer have a valid function, because this point C can now not be mapped to only one value, but there are 2 possible options. Additionally, this point D can now not be assigned to anything. So this function does not have a valid inverse function. Hey, welcome back to the channel. If you're new here, I'm Oliver, a computer science student and tutor. Today, we're covering the concepts behind function inversion. By the end, you'll know exactly when a function can be reversed and when it can't. Before getting into function inversion, we'll ask ourselves, what is a function? So here we have the function f, and it is defined as having the input space x, which is a set, and the output space y, which is also a set. In our example from the introduction, x is the set of all numbers 1 to 4, and y is the set of all letters a to d. But these can theoretically be any sets. They can even be infinite. Now our function says that for every single input, there is exactly one output. So this mapping here would be a valid function. But if we, for example, removed this mapping here, so 1 would not be mapped to anything, this would no longer be a valid function. Additionally, if we added a new line here, then this would also no longer be a valid function because now 4 has 2 values it maps to. So a function is a mapping from one set to another where every input has exactly one output. But now, when can we reverse a function? So we saw in the introduction that this is not invertible because in our output, C and D would not have unique points that they map back to. So essentially, invertibility means that we have a one-to-one mapping. This would be an example of an invertible function. Since for every input, we know exactly what the output will be, and for every output, we know exactly which input it originated from. So in this case, C and D exactly have one input which relates to them. Now we've seen it work in this example, but now let's get a bit more formal and see what has to be true generally for a function to be invertible. For a function to be invertible or reversible, 2 things must be true. The first is that the function must be injective. Injective means that no 2 different inputs share the same output. In this case, our function is not injective because 2 and 3 map to a point C. So the inputs are different, but the output is the same. To fix this, we need to remove this mapping here from 2 to C and map to another element in Y, which is not already an output. In this case, I've chosen D, but mapping it to B would have yielded the same result. In this case, our function is now injective. Formally, we write that for all x and y from our input, if they map to the same output, it must have meant that they are the same input. So if we take 2 things from x and they both land in C, we know that these 2 things must have been equal. The second property that is necessary is that our function is surjective. This means that every single point in the output set, y, is reached. This is not the case for this function because we have a, which is in y, and there is no input in x which maps to this point a. This would be one example of a function that is surjective. In this case, every single point in our output set y is reached, and therefore our function is surjective. Formally, surjective is written like this. So for every single point in our output, there exists an input value which maps to that point. So here we can see for A, that is 1, for B, that is 2, and for C, there is both 3 and 4. We don't care how many map to them, but simply that one exists. So it's fine that 2 of our input elements map to C. And now we come to bijective. And bijective is simply the combination of both of these ideas. So we call a function bijective if it is both injective and surjective. So there is a perfect pairing in this case. 1 is perfectly paired with A, 2 with C, 3 with D, and 4 with B. So every single point in the input is mapped one-to-one with a point in the output. And this is exactly the property that allows for a function to be invertible. It needs to be bijective. So now we know we can reverse a function when it is bijective. The function has to be injective. So if 2 points map to the same output, they are the same. And it needs to be surjective. So every single element in the output is reached by some input. Now here we have an example of a function that is injective but not surjective. So this point B is not the output of any inputs. So it does not get mapped to. The consequence is that if we shift our function from going from x to y to going to y to x, which is what inversion does, our point B is not being mapped to anything. So this would actually not be considered a function, as we've seen at the beginning. And this is a case where our function is surjective but not injective. In this case, our function is also not invertible. The reason being that when we swap this from x to y to from y to x, this element C does not have a point it gets mapped to. It is ambiguous as both 3 and 4 were mapped to it in the original function. So this would also then not be considered a proper function, and therefore the original function is not invertible. As we've seen, the bijective case is invertible, and if we do the swap from x to y and y to x, we just get a one-to-one mapping, so a proper function that maps each of our inputs in y, so these are our new inputs in the inverse function, to exactly one output in the x, which was our original input set. Bijectivity connects directly to matrix invertibility. If you're studying linear algebra, I have a video on that linked here. If you'd like to see more algebra content like this on the channel, let me know in the comments. And as always, thanks for watching.